Hello, everyone. Welcome back to your channel of basic engineering. And as I told you, we are going to do rigid body equilibrium in 3D. I came up with two examples from a statics textbook that I used in the past. And this problem, as you can see, we have a bar, and this bar is connected on one side by a ball and socket support. Here, they spilled some oil, so they are telling you this is a smooth surface, okay? It doesn't prevent motion in any direction. And then we have a cable. Notice I don't care about the support. It's not connected to my rigid body. My rigid body is just that, so it's connected by a tension. And then there is a force of 800 Newton going from point B in the direction of point E. So as we do with any problem, we start by drawing the free body diagram. Okay, so I'm going to try to draw some line here. I'm not going to care about the dimensions or the length. It's not to scale. I have to say these are the 2 or 3 points that I'm concentrating on. Okay, I have point A on the top, point C here, point B. There are also two more points that I'm interested in. Okay, so let's draw. I should have drawn it further there, but I just wanted to have enough space for writing. This is a tension. And then you do some dotted points. And let me say this is point D. Dotted because it's not connected to my rigid body. And then there is a force. So there is F here. F equals 800 Newton. And again, some dotted lines to point D. I will show my X, Y, and Z. But then this is not a complete free body diagram because you cannot solve, right? You don't know anything about, first of all, you don't know where the reactions are. So let's go to A and say I have A sub X, A sub Y, and maybe this is point A and this is A sub Z. Also at C, I have C sub Z, right? Because you cannot move here. Still, it's not complete. Why? Because I don't know the dimensions. How can I express F or these? These are easy, but how do I express F and T in vector form, right? I can't. So please don't forget, point A is 0, 0, 1200 millimeter or 1.2 meter. Let's work with meters because we don't need all these zeros. So I'm going to say 0, 0, 1.2. Notice I have 5 points. Oops, I wrote E, D instead of E. Point B is midway, and they give you a line here and a line there so you know the X and the Y. So the coordinates of this point along the X, it's 400 or 0.4. Along the Y, it's 400 and another 400. Do you see that? It's 0.8. And along the Z, it's half the height, so it's 0.6, half of that. Let's go to C. C is in the XY plane, so its Z value is 0. But C along the X, I moved 400 and 400, so it's 0.8. Along the Y, I moved 400 and 400, that's 800, and another 800, so it's 1600 or 1.6. And finally, point E, no, we still didn't do D. It's on the y-axis, so 0 for x, 0 for z, and 1.6 like C for y. Finally, I have point D, point E, I keep saying D, because I wrote it D originally. Point E also is in the xy plane, so its z value is 0. Along the x, I have 400 and 400, so it's 0.8 like C because they are on the same x coordinate. And its y value is only 400, right? 0.4. And now I have a complete free body diagram. Everybody can use it and solve. Okay, so I can send it to my friends in France and ask them to help me with it. They would be able to do it, right? It doesn't matter where you are if you are using statics. Now, we have to express all the forces, whether known or unknown, in vector form. Okay, or rectangular or component form. So like I did here, I didn't say 0.8i plus 0.4j. I simply wrote 0.8 comma 0.4. So it's up to you. I prefer to write the dimensions in this form and the forces with ijk, but it's a matter of preference. So I would say A because it's a vector, so I'm going to use that. I'm going to say it's AXI plus AYJ plus AZK, right? That's the reaction at A. Then I have another reaction at C, but so I can say C equal CZK. So step number 1, you do a complete free body diagram. Step number 2, you express all your forces, whether known or unknown, in Cartesian vector form. My T, how do I express T? T is a magnitude T, which is unknown, times a unit vector of T, as we know. So I can come to the side and say T starts at 0.4, 0.8, 0.6, and ends at 0, 1.60. So if I subtract the end from the beginning, I will get negative 0.4, positive 0.8, and negative 0.6. Divided by its magnitude. Notice because all of them are divisible by 2, you can simplify by 2 and then multiply by 10 to get rid of the decimal place. This is completely valid, meaning I'm going to multiply by 5. Why 5? I'm multiplying by 10 to get rid of the decimal place and then divide by 2 to simplify. So this would be negative 2, comma, positive 4, comma, negative 3. Now, I have to divide this vector because I created a vector along this direction by its magnitude. And its magnitude is the square root of 2 squared, 4, plus 4 squared, 16, make it 20, plus 3 squared, 9, so over root 29. That's how we do it. So I don't have a 0.4 and a 0.8 and a... Why? Why do I need to use decimals? Okay, then we can have the only thing remaining is our force, right? This is a known force. So it has a magnitude of 800. And again, I'm going to multiply it by a unit vector. What is the unit vector? Again, it starts at 0.4, 0.8, 0.6, the same as that guy, but it ends, so I subtract the tail from the head, the beginning from the final, the initial from the ending, or terminal, 0.8, 0.4, and 0. So when I subtract, I get negative 0.4, I'm sorry, positive 0.4, negative 0.4, negative 0.6. Same logic. Multiply by 5. I want all of them are divisible by 2, and I don't want a decimal place. So multiplying by 5, I get 2, negative 2, negative 3 over the square root of that. 4 plus 4 is 8, plus 9 is 17, so over root 17. See how I didn't need to use a calculator? I don't have to evaluate that. You will see why. It doesn't make any sense. And I have all the ingredients now to start the analysis. I have to write 6 equations in 6 unknowns. Before we continue, and we'll answer this question later, I have 3 unknown reactions for the ball and socket. I have an unknown tension, and I have an unknown Z component of the reaction. That's only 5. Remember, I told you in the previous lecture, in some problems, you may have less than 6, and still this thing is, is stable. It is stable, but it's marginally stable. Meaning, if there is like some air here that, you know, you can move it. You can see that anyway, we'll see it mathematically, hopefully, in the solution. Now I have to write 6 equations in 6 unknowns. Let's start by writing the force equations, or maybe we can leave everything, because notice that the moments, I have to write the moments, right? So let's do the moments equations first. It really doesn't matter which one you use first, but the problem is if you use the force equations first, you see in the summation of the x, meaning if I'm going to use the I components together, so maybe I should have written that as negative 2i plus 4j minus 3k, because I told you I'm going to use it not in rectangular form, but in vector form. But you can see that this is xyz, right? If I do some of the forces in the x, I have the t unknown, the ax unknown. If I do the y, ay unknown, t unknown. If I do the z, az, cz, and the tension unknown. So I can solve anything now. So let's do the moments first. Where do you think I should take the moment? I have five unknowns. Yes, you can write only 3 equations of equilibrium. So it's perfectly fine to take the moment about point A and equate it to 0, right? Because when I take the moment about A, I will have only 2 unknowns, 1 and 2 only. So you say, but I have 3 equations of equilibrium and only 2 unknowns. Yeah, that's what I told you. We only have 5. So maybe one of these won't matter. We'll see. So when I take the moment about A, let me write how we are going to do it. Remember, the moment is R cross F. So if I'm going to say, first of all, I have the tension. Let's say start with the tension since A is already at A. We could have said C, but okay, we do B. So I'm going to say R. I'm taking the moment from A. So RAB cross T plus RAC. Notice all, since this is A, the beginning letter is always A. I see many students reversing that. So be careful. Cross C plus RAB again, cross F. And that equals 0. What is RAB? Again, like we did, RAB is the coordinates of B minus the coordinates of A. Notice. So this would be 0.4, 0.8, negative 0.6. Here you have to be careful. I cannot say I'm going to multiply it by 5 and make them 2. Why? Because when you do that, you are this is a position vector. I have to start here. I have to end there. But this, I created a vector and I just wanted a unit vector of it. That's why I divided by the magnitude. Be careful. We are not going to divide by the magnitude. All what you can do is you can say you can factor out 0.2. Okay, you can factor out 0.2 and then you would say I, J, K, I, J. You do the position vector. So now you can say if I took 0.2, so this would become 2, 4, negative 3, 2, 4. Yes, that's how we simplify it. I want the quantity be inside the determinant to be as simple as possible. So I can use integer values. But what I factored out stays. I cannot delete it. Okay? Cross t, what is t? T is t over root 29. I can leave these at the outside. And enter negative 2, 4, negative 3, negative 2, 4. Plus RAC. What is RAC? Going from here to here, you can see you don't have to write them. You're going from 0 to 0.8. That's an increase of 0.8. From 0 to 1.6, that's an increase of 1.6. From 1.2 to 0, that's a decrease of 1.2. These three numbers are divisible by 0.4. So if I factor out 0.4, that leaves me with I, J, K, I, J. 2, 4, negative 3, 2, 4, negative 3. Wait a second. I did something wrong here. You cannot have the same thing. You're going from A to B. Did I write? Oh, I went A to B. And then here I'm going from A to C. Oh, yeah. Because I factor 0.4. What am I saying? This is exactly the double, right? 2, 4. And then the C itself, I can take CZ out, and it would be 0, 0, 1, 0, 0. Plus the force. The force, again, it goes from B to E. So it's going from 0.4 to 0.8, from 0.8 to 0.4, and from 0.6 to 0. I can factor 0.2 out, and that leaves me with I, J, K, I, J. If I take 0.2, I get 2, negative 3, negative 2, negative 3, 2, negative 2. No, I went, this would be the same as before, right? As point B. So it's 2, 4, negative 3, not negative 2, 4. Right? The position vector is AB, exactly like the tension. So the tension and the force, both of them are 2, 4, negative 3, 2, 4. But this one was doubled, so we pick 0.4 out. Anyway, times I can keep the 800 out. and the root 17 out also, and only enter 2, -2, -3, 2, -2 equals 0. Okay, I know it's so complicated, but everything will become simpler as we go. I wish I had more space. I can use the back, but I want you to see that. So let me get a new piece of paper and write the equations or expand the moments on it. Okay, so let's start with the first moment. 0.2t over the square root of 29 times. I go in this direction, I get -12i plus 6j plus 8k minus, and then I go in this direction, -12i, -6j, -8k. Plus 0.4 cz times 4i 0j 0k minus 0i 2j 0k. Plus 160 over root 17, 0.2 times 800, times -12i minus 6j minus 4k minus 6i -6j positive 8k equals 0. Then we simplify. We get 0.2t over root 29 times -12 minus -12 cancel each other. It's -12 plus 12, so there is no I component. Okay? Alrighty. And then the j, 6 minus -6 is 12j. And then 8 minus -8 is plus 16k. Plus 0.4 cz times 4i minus 2j plus 160 over root 17 times -12 minus 6 is -18i. -6 minus -6, they cancel each other. -4 minus 8 is -12k equals 0. Remember, I have to write 3-moment equation, one in the x, one in the y, one in the z. Now, if you look here, you see that this tension has J and K, and this reaction has I and J. So if I take the moment in the x direction, I can find CZ right away. And if I take the moment in the z direction, I get the tension. I don't have to solve two equations in two unknowns. The y equation is not needed, but you can use it to check your answer. Remember, we only had 5 equations. Sum of the moment in the y here is not an equation. It's not an independent equation. I shouldn't say it's not an equation. It's a dependent one. So let's say summation of the moment, say in the x direction equals 0. This one doesn't have an x. This one has 1.6 cz. And when I move this to the other side, I say equals 160 times 18 over root 17. Wow. So far, I haven't used the calculator. In fact, I can simplify by dividing both sides by 1.6. That would be 100. So I get 1800 over root 17. 1800 divided by the square root of 17. I get 436.6 Newton. If you want to write it in vector form, then you can say if CZ is 436.6, you multiply that by zero point 0.4 times 4 to get the I component times -2 to get the J component. But I already found C sub Z, right? And it's just, I'm sorry, this is the moment. No, C sub Z is just in the K direction, right? So it's if you want to write it in vector form, you say 436.6 K. Then I'm going to take the moment in the z direction, not the y, because in the z direction, I have 0.2 times 16t over root 29. This one doesn't have a k. This one has, if I move it to the right-hand side, it would be 160 times 12 over root 17. Again, 16 and 16 would make that 10. 0.2 2 and 12 would make that 6, so 0.2 would make that 60. So really t would be 600 root 29 divided by root 17. 600 times the square root of 29 over 17. And you get 783. So the tension is 783.7 Newton. And if I want to write it in vector form, I'm going to write it like that. But you don't need to. You see how easy it is? Now I don't need the my, but you can check out to see, for example, if I take the tension, which is this, multiply it by 0.2 over the square root of 29, over the square root of 29, and then multiply that by 12, because that's the J component, right? I get a number. Let's see if I get the negative of that here. So 0.4 times CZ, which is that, times -2. Hopefully I didn't mess it up. Yep, you see, exactly. Well, of course, -349.251. So that's a quick check that we didn't mess up. I was worried that, along the way we did something wrong, but we haven't. And now I go back to the forces. Since I already know everything, I can say, let's use a different color for the force so that you see it. I know this would be a long lecture, so please. So maybe I'll stop here and make a second part for the second problem. Maybe I'll either do it today or tomorrow. I just don't want to make it so long for you. Summation of the forces in the x equals 0. In the x, I have ax, so I take everything that has an I. I have -2 over square root of 29 tension, and I have plus 1600 over root 17 equals 0. Notice when I move them, this would become negative and this would become positive. So let's do that and find a sub x. -2 over the square root of 29 times t, and t was the 783 something, which is this guy, minus 1600 over square root of 17. That seems, is it? The tension, this would be roughly 400, right? Slightly less. And this is 780 meaning 1500, or how come I get, no, that doesn't make sense. Oh, because I said negative. I'm sorry. Yeah, I said it cannot be that high. I'm sorry. This should be positive, right? Because I'm going to move it to the other side. Yeah, that makes much more sense. Negative 97.01 Newton. What the meaning of negative is that AX is going in the negative direction. It's not like that. You don't need to write it, you don't need to correct it here because you already have it there. Then you do the summation of the forces in the y direction and equate it to zero. Now, what do we have? Of course, we have a sub y, and then we don't have a c still. We have 4t, so plus 4t over root 29, and then I have minus 1600 over root 17 equals 0. So now it's the other way around. I'm going to take 1600 over the square root of 17 and then subtract 4 over square root of 29 times times the tension, which is that. And that gives me negative 194.02. Wow, that's exactly twice as much, right? Twice as much as x. And finally, summation of the forces in the z equals 0. I have a sub z, and then I have c sub z, and then I have negative 3t over root 29, and then I have negative 3 times 800, so 2400 over root, oops, I'm sorry, root 17 equals 0. So that would be positive, right? Because I'm going to take 2400 divided by the square root of 17 plus 3 times the tension, which was 700. This guy over the square root of 29. Oh my God, I messed it up. So 2400 over square root of 17, I didn't do that, plus 3 times the tension over the square root of 29 minus c sub z, which is the 400, where is it? Yeah. And I get 582. That's 3 times that, by the way, 0.08 or zero point 0.1 Newton. So if you want to write A as a vector form, you say it's negative 97i minus 194j plus 582k Newton. And we found all our 5 unknowns. Remember, we only needed 5 equations, and there was no moment about the y. Okay, or there was, but they were canceling each other. Okay, I'm sorry it was a long problem to solve, and that's unfortunately what you get when you do 3D rigid body equilibrium, because you have to write everything in vector form. You have to find the moments, write 3 equations of moment and 3 force equations and solve. Sometimes you have to do simultaneous equation, but at least this one was easy because we needed 1 equation because we worked cleverly. So we solved 1 unknown per equation. We didn't have to solve 2 simultaneous equations. Anyway, thanks for your time, and I hope to see you soon for another example of the 3D rigid body equilibrium before we move on. Thanks, and see you soon. Bye.